Hello, hello. Today we're going to be looking at Chapter 5, Lecture 13. We're going to be looking at Learning Objectives 9 and 10. And in here we're going to be looking at Hess's Law. So both of these really um, focus on Hess's Law and the idea of standard enthalpies. So Hess's Law is basically taking advantage of the fact that enthalpy is a state function. So if a reaction is carried out in a series of steps, the change in enthalpy our delta H, which is a state function, for the overall reaction will be equal to the sum of the enthalpy changes of the steps. Okay, so doesn't matter how many steps or paths are taken, our change in enthalpy is just final minus initial. So the number of steps or our path does not matter. That's because we have enthalpy as a state function. It only depends on the final and initial states, our products and our reactants. Okay, so we can, for any process, we can determine the enthalpy for that process as long as we can find a route. Okay, but keep in mind our physical states. Those are important. So our states matter. So I always feel that the easiest way to understand Hess's laws is to go ahead and try out Hess's law. So let's say we have a desire, so we want to know what is the enthalpy for the following reaction. And our reaction is our carbon solid plus gaseous water combine to produce gaseous carbon monoxide plus hydrogen gas. Okay, so we want to know what our delta H of reaction is for this. What we're given is the following sets of reactions. Our carbon solid plus oxygen gas goes to carbon dioxide gas. That has a delta H of reaction equal to negative 393.5 kilojoules. And then we have two carbon monoxide molecules plus an oxygen molecule combine to produce two carbon dioxide molecules, all in the gaseous phase. And that has a delta H of reaction equal to negative 566.0 kilojoules. And then lastly, we have two hydrogen gas molecules plus an oxygen gas molecule reacting to produce two gaseous water molecules. And that is a delta H of reaction of negative 483.6 kilojoules. Now, we can take these three equations, manipulate them, and combine them in order to solve for this equation. So remember, anything that when you add equations together, anything that's on the same side will combine, anything on opposite sides will cancel. So I usually try and find my components of my reaction. So I have my carbon solid right here. And if I look at these three equations, I see that I have carbon solid right here as well. Okay, next thing I want to look at is my water in the gaseous phase. So there's my water in the gaseous phase. And I look over here, and the only reaction that has water in the gaseous phase is right here. Now note that this has 1, this has 2. Then I look some more. Want my carbon monoxide. Here is my carbon monoxide right here. And here's 2 molecules of carbon monoxide here. Now, in this case, we have waters on the wrong side. And in our case of carbon monoxide, we have our carbon monoxides on the wrong side. Our carbon solid is on the correct side. So both of those are on the correct side, but our water molecules and carbon monoxide molecules are on opposite sides. And then our last thing we want to look at is our hydrogen. And there it is right here. And again, these are on opposite sides. And there are 2 of these and only 1 of these. So I'm going to go through and add the equations again down at the bottom, starting with my carbon solid. So both of these are the same amounts and they're on the right side of the equation, so I'm going to write it exactly as it's written above. So my carbon solid plus my oxygen gas produce carbon dioxide gas. And I've done nothing to this equation. I've written it exactly how it was written above. So I'm going to write my delta H exactly as it is written above. Okay, next I look at my water. My water is, I only have 1 in the desired, I have 2 in the given, and it's on the opposite side. So I need to take this equation right here, I need to flip it, and I need to divide by 2. Flip, divide by 2. So when I flip it, anytime you flip an equation, we know that the delta H of the forward reaction is equal to the negative delta H of the reverse reaction. So flipping it, we will flip the sign of our delta H. And then when we divide by 2, when we divide our reaction by 2, we're going to divide our enthalpy by 2. So we're going to put this, flip and divide by 2. We have 1 water molecule now produces 1 molecule of H2 gas. And when we take and we divide 1 by 2, we have 1/2 here. So we're going to take our enthalpy, we're going to flip the sign. So it's going to be positive 483.6 instead of negative, and then divide it by 2. Now, as a note, the H2 had to be flipped and divided by 2 as well, which makes sense. So we've already accounted for our H2 in this one. Last one, when you look at that CO, the CO is supposed to be a product, not a reactant, so we need to flip. And there's only supposed to be one molecule, not two, so we're going to flip and divide by 2 again. Okay, and when we do that, we will have carbon dioxide. Gas goes to carbon monoxide. Gas plus 1/2 O2 gas. And our delta H is going to go from a negative 566 to a positive 566. And we're going to divide it by 2. Okay, now, when we combine these three equations, remember that we want to add things together that are on the same side, subtract that are on the opposite sides. So if we look, here's a carbon dioxide here, a carbon dioxide here. They are on opposite sides, so they will cancel out. Here is an O2 here. Here is an O2 here. They are on the same side, so they will combine. And then they will cancel out with that oxygen on that side. So 1/2 plus 1/2 gives us 1. And then the 1 on our reactant side will cancel the 1s on our product side. Everything else is individual, so we will add them together. Carbon solid plus H2O gas combines to produce H2 gas plus carbon monoxide gas. And we're going to add together all of our delta H's, giving us 131.3 kilojoules. And if we look at this equation, it is the same as the one we first started out with. Carbon solid plus water produces carbon monoxide and hydrogen. So, yay, we are done. And that is Hess's law. Not too bad. Okay, another way we can approach Hess's law is by looking at our enthalpies of formation. So we're going to look at what enthalpies of formation are, and then we're going to apply it to our Hess's law. So enthalpies of formation. These are going to be the formation change or the enthalpy change associated with the formation of a compound from its constituent elements in their native or elemental form. So these elements are in their native or elemental form. So how they exist if not combined with another element. So we give our delta H of formation as delta H subscript F, and then there's a little naught. That naught signifies that we have a standard enthalpy change, and you'll see that naught many times. So this is standard state. So that means we are at 25 degrees Celsius and 1 atmosphere. Okay. So if we wanted the enthalpy information of something like ethanol, we see this is made of carbon and hydrogen and oxygen. Carbon in its native or elemental form is carbon solid. Hydrogen in its native or elemental form is H2 gas. And then oxygen is O2 gas. Okay. So we'd say, okay, carbon solid plus H2 gas plus O2 gas combined to produce ethanol, C2H5OH. And then you'll just put um, stoichiometric coefficients in front of each element to reflect the amount that are found in the compound. So there are 2 carbons, 6 hydrogens, and 1 oxygen. So we're going to put a 2 in front of the carbon, a 3 in front of the hydrogen, and a 1/2 in front of the oxygen. So we can take those 2 oxygens, divide it by 2 to get 1. And if you're dealing with something that you can't multiply a whole number by, so if you need to use a fraction for x, z equals, so if you're trying to get from xz to yz, or sorry, yx, and let's just change up some colors. So to go from something with a subscript to something like that, you would take y, you multiply by your y value, and then you divide by your subscript to get that value. Okay, this enthalpy will be given in a standard enthalpy table, and it'd be given as this right here, negative 277.7 kilojoules, and that's going to be per 1 mole of the substance. So in this case, ethanol. There are huge tables containing standard enthalpies of formation. They are state specific. So our standard enthalpies of formation are state specific. So make sure you choose the correct state before you use these. A very common one that gets messed up is water versus water vapor. They have very different enthalpies of formation. So our delta H of formation for water in the liquid state is negative 285.8 kilojoules, while our delta H of formation of gaseous water is negative 241.8 kilojoules per mole of water. Okay, so let's try one more example, but we're going to use standard enthalpies of formation. So let's say we want the enthalpy for the reaction C3H8 plus 5O2 goes to 3CO2 plus H2O. So we want to solve for that delta H of reaction. And we want the standard state for it. So what is our standard enthalpy of reaction for this reaction using standard heats of formation? So basically, when we see a problem like this, if we're wanting to use standard heats of formation for a reaction, we are going to find all of our compounds and write out their standard enthalpies of formation. Okay, so we would say, okay, we have carbon solid plus hydrogen gas combined to produce our propane. And we just balance that out. 3 there, 4 there, and this value would be given in a table, and its delta H of formation is equal to negative 103.85 kilojoules. This is not a compound, so we don't need to look up its enthalpy of formation. We'll move on to our CO2 plus oxygen gas combined to produce carbon dioxide. 1 carbon on each side, 2 oxygen on each side, so this is already good. This standard enthalpy of formation again would be given in a table, and it is negative 393.5 kilojoules. And then our last one is our water. So we take H2 gas plus O2 gas combines to produce H2O liquid. We want to make sure we have the liquid state because that's what we have there. And we'll put a 1/2 in front of the oxygen to make sure we have the right numbers. That delta H of formation is equal to negative 285.8 kilojoules. We're then going to manipulate these equations in order to get the same values, or the same things on the same side. So with our propane, we're going to flip the equation. With our carbon dioxide, we're going to keep it the same, but we're going to multiply. So we're going to flip the first one. We're going to multiply by 3. And then our last one, we have our water on the correct side as well, but we need to multiply by 4. And what we get, our 3 equations, will look like this. So we flip our first and we flip our sign for our delta H. It's no longer a formation, but it's still standard. And then our next one, we're going to multiply by 3. And we will therefore multiply our formation by 3. And then our last one, multiply by 4. Combine those together. We get our desired equation with the correct amounts and our standard enthalpy of formation or enthalpy of reaction. of negative 2219.9 kilojoules. That is everything for this one. I will see you all later.